Good day, students. Welcome to part 3 on rectangular approximations. Now let's take a look at the instructions for the question. We are to estimate the distance an object with a given time velocity chart covers in the first 10 seconds of movement using left rectangle approximation. Okay, so we are to use this time velocity chart provided right here to estimate the distance covered in the first 10 seconds. So in what way are we going to use LrAM in this calculations? So to do that, let's take a look at some formulas first, and then we can see the justification of our application of LrAM in this situation, all right? So when connecting position, velocity, acceleration, and jerk, we talked about the savants continuum SVAJ representing position, velocity, acceleration, and jerk. And when you go down in this direction, you differentiate, and then you anti-differentiate when going in the other direction. Okay? So let's say you wanted to go from position to velocity. How do you do that? If you have position, if you differentiate position with respect to time, that gives you the velocity function. All right. Now, what if I wanted to get my position isolated? How can I get position using velocity as indicated in this chart right here? So let's start off by multiplying both sides of this equation by dt. Okay. And that yields ds equals v dt. All right, so to get rid of this d component, we're going to anti-differentiate. So we're going to take the antiderivative of both sides of the indefinite integral of both sides, and then we're going to have a cancellation action happening here. This integral, or the antiderivative, cancels out with the derivative. On the left side, we'll have the position s equals the integral of velocity, v dt, okay? So if you integrate the jerk function, you get the acceleration. If you integrate the acceleration function, you get the velocity. And if you integrate the velocity function, you get your position function as indicated here. All right, so if you wanted to find a position from 0 to 10, as indicated in this problem, we're going to calculate the definite integral from 0 to 10 of the velocity function. All right? Since we do not have a velocity function, we are going to be making an approximation as indicated in the problem. We're going to find the value of this definite integral using our left rectangular approximation, okay, from 0 to 10. All right, so what is LrAM? Let's go ahead and review that formula real quick and ascertain its applicability to this situation under consideration here, okay? So LrAM, left rectangular approximation. Let's say we have x of n intervals. It's going to be given by the width times f of, we're going to pick all the points to the left of the right endpoint. Okay, so it's going to look something like this. The width times f of x1 plus f of x2 all the way to the x value before the right endpoint, which we can indicate with x sub n minus 1. Okay? Now you have to be really careful to note that this formula is for n equal subintervals. All right, n equal subintervals. Now let's represent this chart using our interval notation, interval chart, and then see if we can use this formula here. Okay. All right, so we're gonna make an x-axis on my interval. This will help me ascertain my my inputs into my LrAM formula. Okay, so let's say this one is for, let me move it to the left a little bit. All right. All right, so I have a number line. I'm going to partition it we're going from 0 all the way to 11. So let's say this is 0, 0. I'm going to use two boxes here, okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so let's see, that's 11. So let me take out some of these numbers here. Let me take out the 1. Let me take out everything. Okay, so let's see. We're going from 0 all the way to 2. I just want to put the numbers that show up on our chart here so we don't get confused. So we're going from 0 to 2, and then from 2 to 3, and then from 3 to 6, 4, 5, 6, from 6 to 9, 7, 8, 9, from 9 to 10, and then from 10 to 11. Now, what do you notice about this interval that we have right here? This is one interval, this is another interval, this is another interval, this is the next one, and that's the next one. What do you notice about these intervals? Well, let's label them. So this is basically x1, this is x2, x3, x4, x5, x6. Okay? For this problem, we are stopping at 10, so this one is of no consequence, all right? So what do you notice about these intervals? They are not equal, okay? So since the intervals are not equal, that means that we cannot use this formula right here, okay? But the formula we're going to use is similar to this. It just requires W being inserted back and having different values, all right? So in this problem, we're going to have W1. W1 in this case we see is equal to 1, 2 units long. We're going to have a W2. This one is 1 unit long. We're going to have W3, the third interval. We'll have W4, which is 3 units wide, 1 to 3. And then lastly, W5, which is 1 unit long. Okay? So we can see that the widths of our intervals are of varying measures, so we cannot factor them out of the equation, okay? So what formula we're going to use here? So let me first of all indicate what my intervals are. So when we're doing our left rectangular approximation, we're going from x1 to x6. We're picking all the points to the left of the right endpoint, okay? So x1 to x6 is our interval, so all the points to the left of that means we're going to go from x1 all the way to x5. Okay, this is for the left rectangular approximation. So this right here is for our LrAM. Okay, all right, so let's write down the formula of left rectangular approximation when our subintervals are not equal. All right, so LrAM in this situation is going to be with 1 times f of x1 plus with 2 times f of x2, that's for this one right here, plus with 3 times f of x3 plus with 4 times f of x4 plus with 5 times f of x5 for the last triangle, okay? Rectangle. All right, now that we have it all set up, we can now basically use the values from our table to represent the terms in this formula, okay? So left rectangular approximation, the first width is 2 units long, 2 times f of x1. x1 is 0, okay? Plus the second width is 1 unit long times f of x2, which is 2, plus the third width, which is 3 units long, times f of x3. x3 is 3, plus the fourth width, which is 3 units long also, times f of x4, which is 6, plus the fifth width, which is 1 unit long, times f of x5. x5 is 9. All right, this is for left rectangular approximation. All right, so we're going to use our charts to figure out the output here. So 2 times f of 0 is 3. So 2 times 3 plus 1 times f of 2 is 5 plus 3 times f of 3 is 3 plus 3 times f of 6 is 7 plus 1 times f of 9 is 6. Okay, so I got all these outputs using the chart that we have right here. All right, so what we have to do now is just arithmetic, right? Just multiply it out. So 2 times 3 is 6, plus 5, plus 3 times 3 is 9, plus 3 times 7 is 21, 6 times 1 is 6. You add this all together, you get 47 meters. That's the distance, approximate distance, the object with a given chart covers in the first 10 seconds, okay? So let's write this down. Distance covered in the first 10 seconds, which is exactly equal to the integral from 0 to 10 of the velocity function dt, is approximately, using LrAM approximation, is approximately 47 meters using left rectangular approximation. All right, so that's basically what our answer is. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking here for updates to other cool clips such as this. And please post a comment to let me know what you think about this presentation, and do give me a thumbs up if you liked it. More clips can be found on math.serve.com/calculus. Thanks again for watching, and have a wonderful day.